Let's walk through an example. We're going to look at 3 different compounds, and we're going to compare their intermolecular forces to answer the question, which will vaporize at the lowest temperature? So that vaporize at the lowest temperature tells me I'm looking for um, the weakest intermolecular forces because I want to put in less energy to break apart those intermolecular forces. And this is going to be for vaporization as a liquid becomes a gas. All right, so the first step to solving this is I'm going to list the intermolecular forces for each of these molecules. So I'm looking at them. They're all have multiple carbons. They're kind of big. They definitely have electron clouds, so they all have London dispersion forces. So I'm going to abbreviate that LD for London dispersion interactions or London dispersion forces. Cool. So they all have those. If I was to compare them, I think the one with more carbons might be the strongest London dispersion forces, although the bromine is a pretty big atom compared to carbon. So maybe that one is. It's hard to tell, right? So for a lot of this, it's kind of gray area. So I don't try to get too detailed in my comparison. Next, let's look at dipole-dipole interactions. For this, we need to know if something is polar or nonpolar. So I'm going to go through and first identify my polar bonds, and then decide if the molecule is overall polar or nonpolar. So for our first one, we have this carbon-chlorine bond that I know is polar. And then checking my electronegativity chart, bromine is 2.8, carbon is 2.5. So that bromine carbon bond is going to be nonpolar. So it has a small dipole moment, so I can call this one polar. For our next one, and this isn't drawn out all the way, each of these OHs right here are an oxygen bonded to a hydrogen and bonded to a carbon. And so we have a dipole moment for our carbon oxygen bond is polar and our hydrogen oxygen bond is polar. And this is drawn in 2 dimensions, so these look like they cancel out. But remember, our oxygen is actually bent, right? And so it has those 2 lone pairs. We've got the carbon and then the oxygen. So it'll create a dipole, overall dipole moment at those spaces. And then the other half of the molecule is all nonpolar bonds for the carbon and hydrogen. So this will also be polar. All right. Our last one has just carbon-carbon bonds and carbon-hydrogen bonds. Both of those are nonpolar bonds. So this one isn't overall polar. It's going to be nonpolar. So that means my dipole-dipole interactions occur for my 2 molecules that are on the left-hand side. So anything that was polar will also have dipole-dipole interactions between the molecules in a sample. All right. Now let's look at hydrogen bonding. Hydrogen bonding, remember, needs to be an oxygen-hydrogen, nitrogen-hydrogen, or fluorine-hydrogen bond. So in our first one, I see all of my hydrogens are bonded to carbon, so no hydrogen bonding there. In my second one, I have 3 oxygens that are bonded to a hydrogen. So this one has hydrogen bonding interactions. I'll abbreviate hydrogen interactions, HI. And our last one has just hydrogens bonded to carbon. So that's not going to be our hydrogen interaction at all. So looking at this, I would rank these. This one with all the OHs would be our strongest intermolecular forces. And the one that has just London dispersion forces would be our weakest. So to answer the question, which will vaporize at the lowest temperature, I would choose the last one, this C6H, it's probably 14. So it's going to be the one all the way on the right that will vaporize at its lowest temperature. It has the weakest intermolecular forces.